Good afternoon, everybody. My name is Mireia Colina. I with Ana Ruiz, that we are co-leaders of Barcelona Women in Aerospace. Today, we take the opportunity to start a new edition that we want to call Women for Space. This is a series of conference that is aiming that will take place during this course. We are hoping that next year we will organize the second edition. It will be online format, all of them, due to the situations. But the objective of these conferences, these talks, is giving visibility to prominent and inspiring women in the space sector. Okay, today we are proud to present a really amazing talk with Carme Jordi, that is one of our greatest scientific here in the Catalan community. And we organized this conference with the University of the Polytechnic University of Castelldefels and the IEC, that should be the Space Studies Institute of Catalonia. We will, at the beginning, Luis Alonso will start with a presentation about the initiative and about the activities that are performing in Castelldefels. Then Carme will also, as part of Catalan Institute of Space Studies, will introduce a little bit the activities that they are performing, and then she will explain us the Gaia project that will be. Okay, Luis, if you want to start.
Okay, thank you very much. Welcome everybody. I am Luis Alonso. You have introduced I introduced myself. I am the director of the School of Aerospace and Telecommunications Engineering in Castelldefels. We are part of Universitat Politècnica de Catalunya, UPC. And we are very happy because this series of conferences and activities called Women for Space is part of the framework of our 50th anniversary. We are celebrating this academic year, and we are very happy to have a lot of activities, very interesting activities as this one. We thought of a very different celebration of this anniversary, but we have this pandemic situation, this COVID situation, and then we have a lot of activities as planned, but in a different way. So this online way of doing these activities. And I am very proud of present this first edition today of the Women for Space. As it has been already said, this has been organized by our engineering school and also by Women in Aerospace Europe, the local section in Barcelona. And I think that these activities is, this will be one of the list of activities that will be with the objective of having more and more women involved in space and in technology in general. I mean, we have been quite a lot of years working in improving the number. Is not just a position or a problem of having a higher number of women studying technology, maths, and science, but it's also having, more thinking of all this technology and space area in a more attractive way for everyone, and also for women, because probably, it's very difficult to find. It's true that we have been trying to find which is exactly the things that attract women more in the area of technology, and maybe the idea of having a more human, a more connected to people activities of all the technology is, I think, one of the ways to increase the the interest of women in the technology, because technology at the end is also for people. It's not only to work with the things, with the machines, or with the physical inanimated things itself, but also going to or doing things in order to improve the quality of life, improve the life of the people at the end. So this activity is very, very nice in this sense. I think that one of the most attractive areas for women is space. I know a lot of women that are interested in space activities, and maybe with the first idea of going to space to become an astronaut. But it's not, of course, the main thing or the main attractive for women, but also the technology behind. There are a lot of things that we can do or we must learn and do in order to have people in space and all the relative activities around. And today, this first conference will be given by Professor Carme Jordi, which is one of the most prominent and the most prestigious researcher and professor in the area of space. And she's also a very good example, and hopefully it will be very, will be an inspiration for all women and for all people in general, for men and women, of course. So I don't know, Anna or the other organizers, if we want me to introduce Professor Carme Jordi, or you will be introducing her with all the...
If you want to introduce,
okay,
I will do it.
I have taken some notes about her. So Professor Carme Jordi is PhD in physics from the University of Barcelona. She's full professor in the Department of Quantum Physics and Astrophysics in the same university. And she's member of the Institute of Cosmos Science and the Institute of Space Studies in Catalonia, the IEEC. Her research is framed in galactic astronomy and stellar physics, and in particular in the physics characterization of stars and star clusters as tracers of the galaxy disk. So very, very interesting topics. She has participated in some space missions such as IPARCOS and Integral of the European Space Agency, and she's currently involved in the Gaia project also from ESA, from this European Space Agency. And finally, I will say that I think that all these activities in the framework of women in aerospace Europe, and I've seen in the websites, I think it's very good for all the audience that WIA-E has launched a new social networks or social network accounts in Instagram and Facebook, so you can stay connected to these networks and don't miss any detail of this first edition of Women for Space. And hopefully we will be enjoying this conference and also future activities that will be in the framework of Women for Space. So that's all for me. I want to be brief. So let's enjoy this this conference, and okay, I hope all of us we will learn a lot of interesting things. So thank you very much, Professor Carme Jordi, and that's all for me from my side. Thank you.
Okay, should I start, Mireia, Anna, or yeah? Okay, then thanks, Luis, for this introduction and these kind words about me. Actually, well, I am only one of the several women in Catalonia that are working on space. But yeah, thank you for the kind words. I will share my screen. Do you see it?
Yes.
Yeah. Okay. Fine. Then well, my talk is about the stars and the Milky Way, actually, and we want to understand how the galaxy was formed. So we want to understand the history, what's behind our galaxy, our Milky Way galaxy. But before starting with the topic of the talk, I would like to say a few words about the institute that is organizing this meeting as well, this conference as well, the Space Studies of Catalonia. And I would say that this is a research institute that is mainly devoted to the understanding of the cosmos, and this means not only the stars and the galaxies and the cosmology in general, but also the Earth, because the Earth is also part of this universe. So in the Institute there are projects devoted to the astrophysics and also to the Earth observations, and to support that we need some technology. So we have these three main topics that the institute is working on, and the main goal of all of this is fundamental research. We want to understand things, and for doing that we always need new technology on ground or on space. And we are always, the scientists are always pushing and pushing the technology to be at the frontier of pushing the limits, and this makes us so challenging projects. The institute is formed by people in the University of Barcelona, Autónoma University, the Polytechnic University, and CSIC. I am supported by the Generalitat de Catalunya. I am part of this University of Barcelona, but there are people of the three main universities in Catalonia plus CSIC in this institute. And we have several projects in this institute. Some are ground-based facilities, mainly instrumentation in professional telescopes and observatories, and also the institute is running the Montsec Astronomical Observatory here in Lleida. And another main topic is the involvement in space satellites. Some of the projects in this list are in different phases. Some are in study phases, some are in construction phases, and some are in operations. And this is the case of Gaia, the mission that I will talk about today. But as you see, the Institute is involved in many other projects. Now move to the Gaia space mission. And as I said in the title, we want to understand the Milky Way. And the way we see the sky now is very different. The way our ancestors look at the sky, they had only their own eyes to see the sky, and they realized that there is a kind of diffuse band crossing the full sky, which we call the Milky Way. Of course, our ancestors didn't know what this luminous band is, but now we know. And the first step, the first big step to understand this was made by Galileo Galilei, when in the beginning of the 17th century, he started using telescopes to look at the sky. And he discovered many things. He discovered craters on the moon, he discovered the satellites of Jupiter, the spots on the sun's surface, but also he understood that this luminous band that crosses the sky, the Milky Way, is not a diffuse light, but it's actually a lot. There is a lot of stars that it is so crowded of stars that the light of one star confuses with the light of the star, blends with the closest stars, and it looks like a kind of diffuse light. But actually, it is not like that. But it is that we are discrete. We have discrete stars, and as along the centuries, as the telescopes become bigger and bigger and bigger, we had the possibility to see more and more and more stars. So, which is the limit? The stars are occupying the full universe, or they are grouped in some way. This is something that, to reply that question, is something that we need to determine the distances and see how the stars are distributed in the space, so how are distributed in the 3D, in three dimensions. And this is something that at the epoch of Galileo was not feasible. This was not feasible till mid-19th century. So it was some centuries that nobody knew about the distribution of the stars actually. Another big step in the conception of the universe was made by Kant in the 18th century. And he said that actually, since we see a lot of concentration of stars in this Milky Way, it is because we are inside a distribution which is flat. And actually, if we imagine that we are within a flat distribution, distribution of stars, when we are here and we look through the disk, he imagined a kind of disk, we are surrounded for many stars. We see a lot of them. But when we look across the disk, then we see many. We see many less. So actually, this idea of having a quite flattened distribution of stars is the interpretation of what we see in the sky, that we see many of them concentrated in this diffuse band or luminous diffuse band. But he went a next step further and imagined that the Milky Way, what he called the Milky Way, this disk of stars where we live, is not the unique, but there are many others. And he called them islands, universe islands. He imagined actually that even perhaps those islands are not, cannot communicate each other. So there are different universes that cannot interact. Well, now we know that actually he was right in the sense that the universe is plenty of islands of stars, and these islands of stars are the galaxies, what we call today the galaxies. He was not right in the sense that these galaxies do not interact. Actually, we are part of the same universe and we see each other and even we interact. But well, he was in the right way, saying that we have these islands of stars. Then how is our island? How is our galaxy? If we can see the galaxy edge on, we have this flattened distribution. This is what we call the disk. And most of the stars are located in this disk, with a central part which called the bulge, with a high stellar density. And also we have a halo, a stellar halo surrounding the disk with stars, but not as populated as in the disk. And we are embedded into the dark matter halo. So we have not only the matter that we see, the luminous matter, but we also have the dark matter, something that we do not see, but we notice because we have the gravity. We notice the gravity of that material. If we could see the galaxy face on, we could see that in the center we have a bar, and then from the edges of the bar we have these spiral arms. The sun is located more or less there, and although well, these are artistic representations of our galaxy, and we have the idea that the galaxy looks like that, the shape is more or less like that. The details of the structure is not known. Just an example, when I was at the university, we didn't know that we have this bar here. When I was studying the galaxy, the spiral arms started in the very inner center. But now we know that we have the bar, something that we didn't know some decades ago. And even now, we think that perhaps we do not have one bar, but actually we have two bars here. And you see in this representation that these spiral arms are fragmented. We have some bifurcations. So the details of that bifurcations are not clear. So we do not know exactly how many bifurcations we have. There is no consensus on the origin of these spiral arms. If they are persistent, if they change, we do not know. So this is something that, well, we have to learn still. So there is a lot of things to learn in the future. So also we see many, this is not our galaxy, of course, there are other galaxies, but we also see many galaxies interacting, colliding, merging. So it means that these are not islands independent, but they form part of the universe, and they may approach and they may mix and then become another galaxy. Now we know that at the beginning of the universe, the galaxies were very small, and well, they have been accreting and merging and colliding and growing and growing and growing. And we have galaxies now that are big galaxies, but they were not big at the beginning. So they have grown in time by merging and by accreting small galaxies in the surroundings. So our galaxy has experienced the same processes. At the beginning, it was smaller, and later on, it has been growing and growing till the present state. This is another example of these kind of things. So we have here a massive galaxy seen edge on, and we have this kind of band, diffuse light here. And what's that? Then actually, this is a small galaxy that approached this massive one. And because of the tidal forces exerted by this big galaxy, the small one has destroyed it. And all the stars and the gas initially of this galaxy have been spread along the orbit. And slowly, all these stars will mix with this one. And here is not represented, but this one has also an halo here, and this will this small galaxy will become part of the halo, and along the years, this pattern will disappear and will be completely mixed. So we will not know in principle, or will be a bit more difficult to understand which stars belong to which galaxy initially. So then in our galaxy, the process, as I said, is the same. We know that mergers have occurred, and we still know they are occurring currently, because we see hints and patterns of this merging currently. So we see small galaxies that have been merged with our galaxy. But to understand all the process, we need to know how mergers we have had. So it's like doing archaeology of our own galaxy, the same way that the geologists or the people that is studying the changes of the humanity look at the archaeology on the several layers in the geology to understand the process of the formation of the Earth, and so and so. So we need to also, to understand our galaxy, we need to see how our galaxy was before, in several million years before, and to understand all those processes of merging and collisions. And this is basically the goal of Gaia. What we need to do is this a kind of archaeology of our galaxy. And to do that, we need information. Which kind of information we need? Then, we are located more or less there. If we want to understand our galaxy, we need to observe stars in all regions of the galaxy. Of course, we cannot be limited to the solar neighborhood, because if we limit ourselves to the solar neighborhood, it may happen that in the edges of the disk or in the limits of the halo, things that happen are completely different. So we need to look at all directions. We need to look at as much far as possible in order to reach actually the edges of the galaxy, and all directions. So all directions, as many stars as possible and as far as possible. And this means detecting very teeny lights, because when the stars are far away, the apparent luminosity of them is very weak. So we need to have a capacity to detect very tiny, very weak signals. But also, and then which kind of information we need of those stars. So we need to understand how they move, we need to understand where they are, and we need to understand how they are. Because the edges of the star, knowing if they are young or they are old stars, and which is the chemical composition of those stars, can tell us about the origins of those stars. And this together with the motion allows us to make families and to understand which star, which is the origin of each star, and then try to understand if they are they have been originated in our galaxy, or they come from other galaxies that have been merged with us. So the way to determine the distances is a bit an indirect way. So imagine that we are we are the Earth, and we are in an annual motion around the Sun. And when we are in that position, beginning of the year, we see these two stars in these two directions. And after half a year, when we are at the other side of the Sun, we see the same two stars, but in different directions. We have changed our perspective, and changing our perspective looks like the stars are moving. Actually, the stars don't move. It's the observer who is moving. But actually, this motion of the observer makes that apparently the star is describing a kind of ellipse. And as you can see here, this star is near to the Sun, and the motion is wider than in this star, that it is a bit far away, and then the apparent motion is smaller. So when we measure this, the width of this, the amplitude of this motion, we measure an angle, and we know the distance between the observer and the Sun. We can determine the distance doing doing a bit of trigonometry. So we measure the distance through measuring these angles. So these angles are very small because the stars are very far. And to imagine a star at the edge of the disk, this angle is so small and it is at the level of 140 microarcseconds. And when we are at the limit of the bulge, we are at the level of 50 microarcseconds. A microarsecond is, imagine a degree, you divide by 60 minutes, every minute by 60 seconds, and then every second by 1,000,000 parts, you will have a microarsecond. And then this is 50 microarcseconds. So you can imagine how small it is. No? So, and since we have to measure these small angles with precision, we need to be able to detect even more smaller angles. And this is one of the key points of this Gaia mission. I must say that this Gaia mission, that it is of a space mission of the European Space Agency, is currently one of the most important ones in ESA. Is the current flagship, is one of the cornerstones missions in ESA. And it is not only because the impact on all the fields of astrophysics, but also because the success. It is really a mission that it is very successful. As in many cases, Gaia is not the first one doing that. Actually, Gaia is the successor on a previous EPARCOS, a previous mission that was called EPARCOS, also by the European Space Agency. But if Gaia is measuring 2 billion sources, 2 billion stars, EPARCOS was measuring 120,000. And actually, when I started, just after my PhD, I started working for EPARCOS, doing on-ground observations that were auxiliary to the mission. EPARCOS measured distances, parallaxes, and proper motions, but didn't measure any characteristics of the stars. And we needed additional information from ground for the complete science exploitation of the data. Now with 2 billion sources, this is unfeasible, completely unfeasible. And the second generation of this kind of ideas that the European astronomers had to build EPARCOS and that have derived into the Gaia mission is embedded into the same mission. So the same mission do everything. So it measures the positions, the distances, the velocities in the three directions, the 3 dimensions, and also physical properties of the star. So we have now everything in one. And also we have this big change in numbers, so from 120,000 to 2 billion sources. So when EPARCOS finished and the European community started to think in a new mission, so some few colleagues in Barcelona decided to join the mission and to be relevant since the very beginning. So we started working to consolidate the scientific ideas of the mission, and also to develop the instruments, to design the instruments, and to monitor the development along the years. So particularly I'm involved in this mission since 1997, so more than 2 decades. So it's almost part of almost all my life, or professional life. Gaia is not only a big step respect to Hipparcos in terms of numbers, as I said, and in terms of kind of measurements that Gaia does, but also in the precision. To have an illustration, in the case of Hipparcos, these angles that we measure have a precision of 1 millisecond, so 1 arcsecond divided by 1,000 parts, and this is equivalent to look at an elephant walking on the moon seen from the Earth. So can you imagine an elephant walking on the moon seen from here? So this is the angle that you could measure with Hipparcos. But Gaia is much more than that. So it's not an elephant. Gaia sees a butterfly on the moon. So it's like comparing a kind of, we are looking at a man or the eyes of the man, no? Or an euro coin located at the moon seen from the Earth. And this is the capacity that Gaia has. And this is something that has never been done for 2 billion sources. And this is what makes Gaia unique. Important dates in Gaia. So it was launched 7 years ago. The operations started mid-2014. There is a first period of commissioning. We published already two archives, one in 2016 and another one in 2018. And next week, the 3rd of December, so in a week, we will be publishing the 3rd data release that includes the first 34 months of observations. At the end of last year, mid last year, we ended the nominal mission that was 5 years, but because of the success and because the satellite is working very well, ESA approved the extension of the mission till the end of 2020. So we are finishing this year as well. And then we already have been approved for an extension of 2 more years. So the operations will continue till 2022, the end of 2022. And also in 2022, probably before summer, we will be publishing additional information of these stars that we will publish next week. So here we will publish motions and distances and parallaxes. And here we will be publishing temperatures and gravities, classification of what's a star, what's a galaxy, also velocities in the line of sight. So we will be adding products to these sources. In 2025, we expect to publish the data related with these 5 years of observations. And we also will reach the end of the fuel capacity. So we will probably, well, if we are approved for a new extension, that I hope so, the fuel will be exhausted in 2025. So this is really the end of the mission. And then we will probably need about 5 years more to produce the final catalog with all the data of the more than 10 years of observations. Then how Gaia operates. Gaia has 2 telescopes. The 2 telescopes are inside this tent, and this is a sun shield to avoid that the light of the sun enters into the telescopes. So each of the telescope is pointing to a different position on the sky. So each telescope is seeing different stars. And the satellite revolves continuously. So we are changing the vision of the stars continuously as well. So imagine the stars of one telescope. The light is reflected into 6 mirrors inside this tent, and finally it reaches the focal plane. And the focal plane is composed by 106 digital cameras. And well, the stars of seen by one telescope are, of course, projected on the focal plane. There is a sky mapper here to detect them. And then from the position here, we can foresee at what time they will cross the rest of the focal plane. As well, the other telescope is looking at a different direction of the sky. The stars are also projected on the focal plane simultaneously. So we have the overlap of the two telescopes in the same focal plane. And as it is revolving around its axis, the stars are passing and passing and passing here. So we are at a rate of about 78 billion observations every day. So we select a small part of the camera. We do not download all the information. We only select the data around the stars, and this is stored on board because, well, full of the sky is empty. There is no information, and so we do not need to occupy the memory on board with no information. So we select always just a small window around each star, and we store that on board. So the stars are going through all the chips, all the cameras, and we have a small window for each camera. So we have several observations in this part, which is the astrometric part. Then when it reaches these two strips of cameras, we have two prisms on top, one to decompose the light in the blue part and the red part, and then this gives us information of the color of the star and the temperature of the star, which is important for the classification. And here we have several prisms on top, and the light is more dispersed, and we see these dark lines here that allow us to determine the velocity in the light of sight to know if the star is approaching or receding from the sun. Everything is codified and digitalized on board, and then later on is sent to the Earth. And okay, this was one star, but actually we have many stars per second on the focal plane. As I said before, 78 million observations per day in average. There are days with more observations and days with less observations. And we are with the two telescopes, and then we are doing all the observations. And every day the satellite through the antenna is downloading the data to the antennas in New Norcia, in Argentina, and in Spain. And the information is collected continuously. So this is an image of the focal plane when it was already assembled, but it's still, it was on ground. And we have this main part here, which is the astrometric part, and then these two, on top of these two, there are the prisms, and part of these 12 cameras here, we have the spectrograph for the radial velocities. And also to give you an idea of the challenging, I'm sorry, is my phone, of the challenging technology of Gaia. Here you have one of the two main mirrors, and the main mirror is rectangular, is about 1.5 meters by 0.5 meter. And to have an idea of the precision that we need in the polishing, you can imagine that this mirror is at the level of the Ocean Atlantic. And you can imagine the waves on the Ocean Atlantic. So then the precision in the polishing is about 10 nanometers. And this is equivalent to have very small, few centimeters in the whole Ocean Atlantic. So you can imagine the precision on this polishing. It is quite difficult to do. It is also difficult to keep the satellite at the thermal stability that we need at the level of millikelvins. And also the satellite material is made in silicon carbide to ensure that we do not have changes due to this temperature. So it's really technologic from the point of view of technology is a really quite amazing mission. This is and a video of how the satellite is scanning the sky and how we are collecting data. Nowadays, we have more than 1 trillion observations, individual observations collected already. Of course, all this data needs a big consortium to process, to understand, and to produce the catalogs that we publish to for the community. And this consortium is composed by about 400, 450 people all around Europe in several institutes and universities. And it is structured in several units. And we are part of this structure. Also, we have several committees that control, that make and monitor how the things are developing from the point of view of operations and from the point of view also of the processing of the data. And this is the Gaia science team, which is the advisory body for the project scientists at ESA. And I am belonging to this science team since 2002. So for some time already. So I have been looking how this mission has developed and how the industry has been success to face all the challenges that the scientists put on them. Also, there is an executive committee that is the representation of all this consortium, and Xavier Luri in my team also is part of this executive committee. And then we have 2 networks for science exploitation, great at the European level, and then we have another one at the Spanish level. And Francesca Figueras is leading this Spanish network. I am part of this great network here. And we started in Gaia with a small team in Barcelona, but now we are not so small. We are a group of about 25 people, multidisciplinary. We have engineers, we have scientists. We are part of this consortium, and we are in these units, and we are also, as I said before, part of these top level committees that look at the development of the mission. So we are quite happy and quite proud of being able to do that, and the success of the mission. To have an idea of how difficult is the data processing, only for this part here, which is the interpretation of the images that we receive from the satellite, we are part of the 6 data centers that process the data. And in Barcelona, we use the Mare Nostrum supercomputer of the Barcelona Supercomputing Center. And only for producing this archive that will be published next week, we have used 1 zeta flop. So this meaning 10 to the power of 21st flops of computation. So this is, to have an idea of the computing power needed for producing a release. And this is not only the full release, but only this part here. One of the duties that we have in this part is to identify which observations belong to each source. So because at one time we are scanning the sky in this direction, and another time we scan the sky in another direction, and another epoch we scan the sky in another direction. And we need to understand that these 3 observations belong to the same star, these 3 to the other star, and these 3 to another star. And we need to do that because we need to interpret how the stars move on the sky. The stars move because they move, and the stars do this kind of loops because the observer is going annually around the sun. And having observations in different positions with time on this path that the star describes on the sky is how we can determine how the star moves, and the amplitude of these loops provides the information of those angles that I was telling before, the parallax that is related with the distance. So we need to have all the stars, all the observations that belong to a star, identified together in order to be able to identify, to derive the motions and the parallaxes of each star. We don't want to confuse stars, observations of this star with the observations of this star, although they may cross at some point, because we need to be able to identify the motion of each one, of each star. So this is quite difficult, especially when we have dense positions, regions of the sky with high stellar density, or we are in the core of the nucleus of globular clusters, and so on. So this is a map of the sky that we did with the second release. This will be improved the next week. I have to say that this is not an image we are used to go to the sky and take a picture. This is not a picture of the sky, because we only download to the Earth small windows for each star, for each source. So here, this map has been constructed by putting by adding one dot to each position. We have seen a source, and so of course, when we have more, the areas where we have more sources is more brilliant, and the areas where we have less sources is more dark. But I would like to emphasize that this is not a picture. It's a map with points, with almost 2 billion points in this galaxy. You can identify concentrations of stars here. Here is the center of the galaxy, and those concentrations here actually are the 2 Magellanic Clouds, small galaxies, satellite galaxies of the Milky Way. Here we have big concentrations of stars. These are globular clusters, but here we have the small Magellanic Cloud, and here we have the large Magellanic Cloud with a bar also, and with the spiral arms. And these are 2 galaxies, small galaxies surrounding our own galaxy. And we have interactions. We are disrupting our Milky Way is disrupting these 2 galaxies, these 2 satellite galaxies. If I do a zoom in this central part here, in these obscured parts here, so what we see is that, well, it kind of missing stars. So there are no stars here, it's completely black. Why do not have stars here? So do not have stars here because we have dust between the stars and us. And this dust blocks the light. So the stars that are behind the dust, when the light reaches the dust absorbs this light and re-emits in another wavelength, in infrared, and we do not see anymore this light invisible. So Gaia is not designed to detect the dust. It's not designed to see the dust, but only to see stars and point-like sources. Here we have some clusters as well. But since in the places where we do not see a star, we have a hint that there is dust. So it's an indirect way to detect in which regions we have more dust or less dust. As said before, we do not only determine where the stars are located, but also how the stars move. And sorry. I don't know what happens with my phone. Here we have a group of stars. We are traveling around the space, and because it is, we know the distances, we can move through the stars. And we have here a group of stars, which is called is named the WIA-E. And now the camera will the simulation will turn a bit to identify a bit better these stars against the background. The background changes, but these stars are the same. And now we will put an arrow that explains how they move. So here we have some stars that move differently and some that move in that way. So this is a way that we have to determine which stars are really part of the group. And this group was born from a giant molecular cloud that fragmented into stars, and the stars are always born in groups. And identifying these families of stars that move together and that located in a given position and move together is a way to determine which stars are born together as well. So this is a way that we have to determine the origin of the stars. We have with Gaia in year 2, our group has detected more than 600 new clusters. Before Gaia, we knew about 1,500, something like that, and we have discovered 600 more. And it is because we are able to identify these groups of stars that move together. And we also have seen that in very young clusters, we have a lot of structure. So we have some substructures, some areas where we have a much more dense number of stars. And in this case, we have this also a kind of ring. And the way the giant molecular cloud is fragmented into stars is something that it is not well understood, because some of those stars will die very quickly and will eject, as supernovae will eject part of the material to the surroundings, and this may trigger as a kind of second generation of stars in the same cloud. And how this supernova feedback modifies the formation of stars is something not very well understood at a small scale. And the people that do theory on that and do modeling of the star formation needs information, needs some contrast with observations. And this is what Gaia provides, and this is what we have been able to detect with this small group and substructures within the clusters. Another important thing is about these mergers. I started talking about the mergers of the galaxies and the way the galaxy forms. And look at this simulation. This is we have a flat galaxy, our galaxy, let us say, and then we have a small galaxy that approaches us, and the interaction of this galaxy with our own galaxy completely disturbs the orbits of our galaxy, of our stars in the disk. The disk is not flat anymore. It starts having the stars are spread across, and the orbits change completely. So, and as the time passes, our flat disk becomes thicker and thicker. So this is what, if we see how the velocities across perpendicular to the plane evolve with time, we see this kind of structure. So this is a velocity across as a function of the position. And this simulation predicts that we have to have this kind of a spiral in this structure, the velocity perpendicular to the plane and the position perpendicular to the plane. We start with something which is quite uniform, and then as the time passes, here you have the time, as the time passes, this spiral becomes more and more complex. So what we have seen in the data is this spiral. And so you see that this spiral perfectly matches this theory. And what we see then in this data, this is real data, what we see in this real data can be interpreted perfectly with the provoked by the passage of a minor galaxy around us about 300–900 million years ago. And this has been identified with the Sagittarius dwarf galaxy that it is currently being merged with our own galaxy. And this is a paper that was published in Nature just after the publication of the second catalog by Teresa and Toja in our team and people in our team. And this is one of the success, the first time we see the perturbation in our disk due to this merging. Also, we may have some mergers with galaxies that are a bit bigger. And in this case, you have the simulation of the merger with a galaxy which is about the size of the small Magellanic Cloud, a bit larger. And also, it perturbs completely our galaxy, and it is destroyed. The small galaxy is destroyed and has a motion completely different of the revolution of our stars in the disk around the center of the galaxy. And in this case, we also have seen that pattern of orbits in our observations. We see a group of stars, these ones identified here in red color, that have retrograde orbits and that have a chemical composition completely different of the stars of our disk, of the stars of our disk. And this chemical composition different means that the origin is different. And then it means that we have had experience, and our galaxy has experienced another merger some time ago. In this case, it's much, well, it is earlier in the formation of our galaxy. It was 10 billion years ago. 10 billion years ago, but after 10 billion years, we still have a way to detect which stars belong to our galaxy and which stars come from the other galaxy. So after 10 billions, there is still signature. Everything has not been washed up. And this is because we are able to detect the chemical composition and the motions and the distances. All this is what makes this investigation successful. If you imagine the Earth and the other planets surrounding the Sun, we are all attracted by the gravity of the Sun, and we can measure the mass of the Sun because of the orbits of the Earth and Jupiter and Saturn around the Sun. The same way, we can see the small galaxies that are satellite of our galaxy that are just orbiting our Milky Way. And these orbits of these satellites, of these small galaxies around the Milky Way, allow us to determine the mass of the Milky Way. And this has allowed us to derive this mass. We have about 10 to 12 solar masses in our galaxy. And this is much larger. This is 10 times more than the mass of the stars. The mass of the stars is about 10 to 10, but 10 to 11, sorry. But the mass of the galaxy is 10 to 12, so there is a factor 10, and this is the dark matter. So thanks to the orbits of those galaxies calculated with Gaia data, we are able to account, we are able to derive the amount of dark matter that we have in our galaxy, and it is about a factor 10 of the number of the stars, masses of the stars. So I will finish here, basically saying that Gaia is unique, as I said already along my talk, because of the limiting magnitude. So it means that we can really detect very faint objects. Also in the number of the stars, because it is about 2 billion, we have stars, and we have also small galaxies, and we have solar system bodies, and everything that it is point-like is observed. As I said before, it is an exquisite precision of 15 microseconds, never reached before at such level of number of sources. And we have impact on all fields of astrophysics. It's not only archaeology of the galaxy, but also, as I said, formation of stars, understanding the properties of the stars, the evolution of the stars, the solar system. And well, you can measure this impact and this success through with the papers, the number of papers that have been published, and this amounts more than 4,000 papers, most of them published since 2018, because it is the release of the proper motions and parallaxes for 1 billion, more than 1 billion sources. And nowadays, everybody around the world is using. Well, almost everybody around the world is using Gaia data, and it is the reference catalog for all projects on ground and projects also for the space. Other missions are based also on Gaia, or will be based on Gaia stars, Gaia positions and motions. I have listed here several links that perhaps you are interested to follow, to learn a bit more on Gaia. And there are images, videos, information for scientists, outreach information for public in general. We have also here our web page in Barcelona. And I would like to finish just thanking you, your attendance, and reminding that, well, next week you have an appointment. If you have any questions that I can answer, I will be happy to do that. Thanks for attention.
Thank you, Carme. We are really proud that you have been our first speaker in this series of conferences. And as Gaia, you are a unique source of inspiration. Thank you. We have some questions, okay? First, we want to ask, we have prepared as a common questions that we want to ask to all speakers in these areas. Then we will proceed with the questions that we have some questions already in the chat. Okay. Okay, the first question that I want to ask you is, since you were a girl, you already knew what you would like to become when you grow up?
Not really. Even when I was a child, I didn't know that I could be able to go to the university. But okay, when I was at the secondary school, I was passionate by maths and physics, and at the end I decided to enter a university and did physics. So I have a PhD in physics. And when I was at the university, my colleagues were astronomers, amateur astronomers, and then I started learning about the stars, and at the end, well, this is my profession.
And you are doing really great. Another question, do you think that your career would have been easier if you were a man? It's a tricky question.
Yeah, it's a tricky question. Probably yes. I should say that I never noticed a strong bias towards me because I am a woman. But probably it is something there is something in the inconscient, no? So there is a general culture, the society, probably my limitations. I put my limitations, my own limitations myself. So yeah, probably my mind would have been different if I am a man.
Mm-hmm, absolutely.
And then probably I would have behaved differently.
Yeah.
Yeah.
Yeah, it's a really good answer, because it's something that we are trying to change with this project, that is Women in Aerospace. Just, do you have how you value aerospace sector, both positive or negatives, and the impact on the society? In that case, for Gaia mainly, which kind do you think that Gaia could impact the society?
Well, there are several things. No? One is the fundamental knowledge of the universe. It's something that everybody asks themselves. What is our origin? Why we are here? How the universe has formed? How the life has originated in the Earth? So understanding the formation of the galaxies, the formation of the stars, is something towards the well, to answering the big questions that the humanity puts itself. But also from the point of view of technology, every mission needs to develop new technology, new materials, new communications, new data processing, and pushing this to the limits always has a return to the community, to the society in general. So it's okay, knowledge, but also technology. And in the case of Gaia, is the antennas, is the silicon carbide material for the construction, is the data processing, which is quite difficult, and so all these kind of things that are developed around Gaia have impact on other missions in the daily life, and so on.
Mm-hmm. Yeah, it's true that the one of the main challenges in space are also challenges for the society, and help us to push to go ahead. And last question from our side: which message do you want to transmit to the new generations?
The new generations. I'm very sorry.
Don't worry, you're famous.
No. Someone that it is looking for me. The new generations. I would recommend, especially the girls, but to everybody in general, that don't put barriers for you. So explore your limits. Try to be critical with the news. When you learn, when you read things or your teacher says something, try to go a step further. Try to understand, not to memorize, but to understand things, to be critical, to interpret results, to interpret what you see. To become a scientist, you have to put questions yourself and try to reply those questions by testing if you are right or not. So making hypotheses, making theories, and then trying to confirm or to reject those theories. So yeah, the astronomy is something enthusiastic. You have possibilities to observe the sky, to travel, to work in collaboration with many colleagues around the world. And actually, it's something that is learning about the universe is fascinating, and working in these space missions is also fascinating. So just push for what you want.
Thank you. Anna will proceed to ask some questions that are on the chat.
Yes, we have some questions, Carme. Ana Maria says, which are the expectations as improvement respect to the ground telescope?
To the ground telescope?
Yes.
Observing from the ground has a limitation, and it is mainly the atmosphere. We have an atmosphere, and the light of the stars have to go through the atmosphere before reaching the telescopes on ground. And this atmosphere introduces a lot of perturbations. First, it absorbs light, so we cannot see all the colors of the light. We cannot see all radiation. We only see part of the electromagnetic radiation of the source. And also this perturbation of the sky limits quite a lot the possibilities to reach this precision. This precision of 15 microseconds is not reachable from ground because of the perturbations of the images due to the atmosphere. Also, on ground, we cannot do the full sky with one telescope, because if it is in the northern hemisphere, we see half of the sky. If we're in the south, we have seen the other half. So having one telescope to have observations homogeneous, we need to go to the space, because it's the only way to have access to the full sky. And yeah, well, basically is that we need the full sky, and we need this high precision. This is only achievable in the Gaia case. Is only achievable from space.
Thanks, Carme. The next question, Edu asks, could exoplanets be detected indirectly studying the variations on a star's luminosity or position?
Yes, right, perfectly right. So we are observing every star about 80, in average of 80 times in 5 years. So comparing the observations of this star in one epoch and another epoch, so we can detect if at some point we have a decrease of the light, and we have a decrease of the light that repeats and repeats and repeats. Then this is a hint that we have an eclipse, that there is a transit of an object that from time to time eclipses, obscures part of the star, and we have a decrease of the light. There is another way to detect indirectly exoplanets around the stars, and it is that if we have a planet that is surrounding a star, actually it's a kind of a two-body problem, and the star is also moving. So we have a center of mass, and the planet moves around the center of mass, and the star moves around the center of mass. So we cannot see the planet, but we see the stars surrounding a center of mass. And then this is a hint that there is something else, and if we can determine the mass of the companion, then this is again an idea of we have another star, or we have a brown dwarf, or we have a planet. And this is something that, well, we knew very few planets with this method, but with Gaia we can determine many more. And for that, as longer the time the Gaia is in operation, the better, because we need to see the repetitions. And then we have a mission that only lasts 5 years. We cannot detect these deviations from around the center of mass. But if we have 10 years, then we have more data, we have more precise data, and then we are much more able to detect that the stars that do not follow this kind of patterns here, but we have a disturbation around this due to the motion, to the presence of a planet. But as I said, this is quite limited now. But if we can go to 10 years mission, then we will have more success.
Okay, Carme, thanks. And there is a last question from David. From before Gaia's launch, it was commented that it would lead to the discovery of many thousand of extrasolar planets through astrometric methods. However, no information has arisen on these results. Is the next data release going to include these results? What can be said up to now about planets finding thanks to Gaia?
Well, this question is related with the previous one, actually. So no, in this release that we will publish next week, this will not include information about exoplanets yet. But yeah, in the next release, we will have more period of time. Let me go to the timeline here. So in this release, we will have 66 months, and so we will have been able probably to detect some astrometric planets. In this now we have only 34 months, and it is a limited time to determine this presence of planets around, looking at the star moving around the center of mass that I was talking before. But we expect that in this data release 4, with 66 months, then we will be able to detect those astrometric planets.
Okay, thanks, Carme. So we finished this conference. Thanks, Carme, for your participation. And it was a pleasure that you are the first woman in this conference series of Women for Space. And there will be some more conference next year, and we will announce in the social networks. And if you have some questions, you can ask us through mail or to the Instagram or Facebook.
Thank you, Anna. Thank you, everybody, to be part of this project. And we are waiting for you to the next conference and the next projects. Be healthy.
Thank you to all for your attendance and for inviting me to be the first in this series of talks that I'm sure that all will be very, very interesting. Thank you.
Thank you, Carme.
Bye.